Hi, John Borchardt at Sandia National Laboratories in Albuquerque, New Mexico. I want to share with you today analysis of U-slot patch with characteristic mode analysis and couple mode theory. Before I get started, I want to acknowledge my co-author Tyler LaPointe, and I also want to say that we've got a paper out with a lot of the details that I'm going to present, so I'll give you a link to that and citation at the end. Brief outline of the talk. I need to introduce multi-mode patches and the U-slot patch, and also briefly introduce couple mode theory. But my real goal for the talk is to convince you that couple mode theory is relevant to the U-slot patch, and I'm going to do that with CMA. So patch antennas are great, a lot of great things about them, but one of the main drawbacks of patch antennas is narrow bandwidth. So I want to introduce some ideas with a simple patch antenna here on the left, and you can have a single mode with current flowing a single way. That produces a impedance locus on the Smith chart, passes near the center, and that produces a single dip log magnitude response. It's got here a relatively narrow bandwidth. You can model this by a little bit of probe inductance in series with the cavity mode, which is an RLC resonator. And you can approximate the impedance of an RLC resonator with this expression. And what this expression shows is that your ability to match to 50 ohms is dominated by actually the reactive part. It's a change in the reactive part. And the parameter Q here, the quality factor, is sort of a scaling parameter that tells you how fast does the reactance change as you detune away from the resonant frequency. And so Q is fixed for a given antenna size through Chu limit and so forth. So another way to think about this is that Q is kind of like the speed at which you're driving along this path. Again, it modulates how fast does the reactance change with change in frequency. So given that a patch of a certain size is what it is, the one way to get more bandwidth is to add a second mode. So you can have a second mode with current going maybe along this direction. And the way you model that is by adding a second parallel resonator in series, and which has this expression. And now there can be two different resonant frequencies. What that does in the Smith chart is it creates an impedance locus like this with a little cusp. And the log magnitude response shows this kind of W-shaped feature here. But what you notice is that the bandwidth is now bigger than it was before. If you continue to separate those resonant frequencies, you develop a loop in the Smith chart in the impedance locus. And again, this Q parameter is kind of telling you how fast you're driving along this impedance locus. But if you make more road, so to speak, you're still moving the same speed, but you're staying near the center of the Smith chart for longer, and that produces a more wideband impedance match, which you see here. This is twice as wide as it was originally. So adding a second resonance is an important technique for increasing patch antenna bandwidth. This has historically been done by just adding a second resonator. So for stack patches, you start with a patch, you add a second one on top, they're coupled, you get a loop in the Smith chart and broad bandwidth. For coplanar parasitic patches, you have a driven patch, you add another patch right next to it, one, maybe two, and you get a loop in the Smith chart and broad impedance bandwidth. In 1995, Hyun and Lee introduced a very interesting geometry. It was just a rectangular patch with this U-shaped slot in it. And Hyun and Lee found that broadened the bandwidth quite a bit. And lo and behold, the impedance locus has got this loop in the Smith chart. So the U-slot patch is very, very successful and very popular in the literature, but it's never been 100% clear exactly what physics are going on here, or exactly how to design one of these things. So that's basically what this talk addresses. I know everybody here is familiar with CMA, but I want to remind you of a few details about CMA with an excitation, and I want to do that through another simple example of a half-meter long dipole. So you can calculate the modes of the structure, and you get the usual, half wave, full wave, and 3/2 wave current variation on the dipole. That's modes 1, 2, and 3 here. And you get those regardless of whether there's an excitation. But when you add an excitation, it allows you to calculate a few additional very interesting quantities that we're going to use later in this talk. And one of them is the modal weighting coefficient, which is given by this expression here. The modal weighting coefficient tells you what proportion each mode exists on an antenna with an excitation. So you've got the modes, and then you've got their weights, and that comprises the total current. So I'm plotting that here for half-wave dipole. Down to the lower left, I'm plotting modal weighting coefficient versus frequency. And what we see is that that first half-wave mode peaks right around 300 megahertz, where it's resonant. And the 3 half-wave mode also peaks around 3 times that frequency. But the interesting thing we see is that that second mode, because it has a null in the current distribution at the excitation, is never really excited strongly. And so the way I think about this is that the characteristic modes tell you what all the possibilities are, but it's the modal weighting coefficients that tell you what really is happening on any given antenna structure. When you have an excitation, you can also calculate the modal admittances, which are these terms here. And the total admittance is the sum of those modal admittance terms, which implies that the equivalent circuit is a parallel combination of modal admittances. Coupled mode theory is an old idea that tells us how to analyze a system of 2 coupled resonators. And I'll use another simple example here of 2 mechanical pendulums that are swinging. The pendulums could have different resonant frequencies, but we're gonna join them with a rubber band or a spring. And coupled mode theory tells us that we can analyze the motion of that coupled system in terms of 2 eigenmodes. And there's an in-phase mode where the pendulums swing together, and an anti-phase mode where the pendulums swing exactly opposite. And in the in-phase mode, the rubber band is not stretched at all, whereas in the anti-phase mode, the rubber band is stretched. And the net effect of having the rubber band acting on one mode and not the other is that the resonant frequencies are different, and that's this omega minus and this omega plus here. You can calculate those frequencies with a simple formula that says the in-phase and anti-phase mode frequencies are the average frequency plus and minus the Pythagorean sum of this difference term plus an unnormalized coupling coefficient. Well, if the uncoupled frequencies are the same, omega 1 equals omega 2, this term goes away, and this equation simplifies down to the in-phase and anti-phase mode frequencies are the average frequency plus and minus the unnormalized coupling coefficient. I'm plotting here on the left what's typical behavior for these coupled systems, where I'm plotting the frequency of the in-phase and anti-phase mode versus a normalized coupling coefficient kappa. And what you see, of course, when kappa is 0, there is no coupling, and so the frequencies are both identical. But as you increase kappa, the frequency separation between the anti-phase and in-phase modes increases linearly. And this is real typical behavior of coupled mode theory. Coupled mode theory occurs in all branches of physics and electrical engineering, in slow wave structures, in particle physics, and filter designers. Filter designers call this frequency splitting behavior. But there's a real nice video on YouTube here. It's real short. It's only 60 seconds long that explains coupled mode theory really nicely. I invite you to check that out. So we take the Hunan-Lee U-slot geometry and put it into FICO. We're using an infinite ground plane. I model the probe as a square cross section just to save unknowns, but it doesn't really matter. You can see there's an excitation here at the base of the probe. So we run that CMA in FICO, and you get out eigenvalues. And this is kind of a complicated eigenvalue spectrum. There's some inductive modes that we don't usually pay too much attention to, but here in the impedance bandwidth, which is about 800 to 1050 megahertz, there's several modes that are resonant and potentially interesting. So when you look at the modal weighting coefficients, you see that it's really modes 1 and mode 3 that are the significant modes throughout the impedance bandwidth. The rest of these modes are below 10 to the minus 5, and mode 6 is a little bit of a red herring, but don't get distracted by it. If you look at the modal weighting coefficients, you can see that modes 1 and 3 are the important ones. And if we look at this from an admittance standpoint, we see much the same story. So the red curve here is the driven admittance that's got a loop in the Smith chart. And the blue and green curves are the in-phase and anti-phase modes. And what we see here is that they're actually stagger tuned. The mode 1 is resonant at a lower frequency, and mode 3 is resonant at a higher frequency. So they're stagger tuned. And when you put these stagger tuned resonators in parallel, they create this magenta curve, which again closely replicates the driven admittance, and has that loop in the Smith chart that's the key to broad bandwidth and is the hallmark of multimodal patches. So the patterns of both these modes are good. They're both broadside and copolarized in the E-plane. So that means that as we move throughout the impedance bandwidth and we go from exciting more of one mode to more of the other mode, that the radiation pattern is going to remain stable. So what are these modes? Here I'm plotting the eigenvectors of mode 1 and 3, and those are the currents, and you see there's a lot of swirling and curling. These are very complicated current distributions, and it's very hard to understand what's going on. So our insight that coupled mode theory was relevant here was made possible by plotting not the currents, but the integrals of the currents, which are the charges. And when you look at these two charge distributions, you see that these represent in-phase and anti-phase modes. So let me draw some pluses and minuses on here and take you through this. So for mode 1, you've got charge accumulation on the edge of the patch and on the edge of the slot. But in mode 1, these distributions are aligned, minus to plus and minus to plus. In mode 3, these charge distributions are oppositely aligned. So from minus to plus and minus to plus, they're pointing the opposite way. So this allowed us to understand that mode 1 and 3 are in-phase and anti-phase modes. And this is really suggestive that coupled mode theory is relevant to the U-slot patch. We did this numerical experiment where we varied the width of the U-slot while keeping the total length constant. And the idea here is that the resonances won't be changing very much, but as we increase the width of the U, that will increase the total amount of patch current that the U-slot will intercept. And therefore the coupling should get bigger. And so that's exactly what we see. Here on the left, I'm plotting the CMA resonant frequencies of the full structure versus the width of the U-slot. And we see this very characteristic frequency splitting behavior that is the hallmark of coupled mode theory. Now, we can take this a little bit further, and we have from coupled mode theory, we have this little equation that tells you how to calculate a normalized coupling coefficient, and we just postulate that the normalized coupling coefficient is equal to the geometric ratio, the width of the U to the width of the patch. And we see that those coupling coefficients actually overlie pretty nicely. And we'll take it one step further. We've got our equation from coupled mode theory that tells us how to calculate the in-phase and anti-phase modes. We can take our normalized coupling coefficient, unnormalize it by multiplying by omega naught over 2, and put it into this expression, and that results in what you see right here. And these coupled mode theory predictions overlie the CMA calculations actually very nicely. So again, this is now quantitative evidence that coupled mode theory models the resonances of the U-slot patch well. So the next question you ask is, okay, well, if we have coupled resonances, what are the individual resonators? And it's pretty obvious that the patch is one, and it's pretty easy to take the U-slot out of the patch. When you do that and run CMA on just the patch by itself, you get a resonance at 946 megahertz. That's right in the middle of the CMA resonances of the coupled structure. That having been said, it's a lot easier to take the slot out of the patch than it is to take the patch out of the slot. And so a lot of people have just taken that U-slot shape and put it in infinite ground plane. You calculate the resonant frequency, which is approximately lambda over 2, and you come up with 640 megahertz. And that's way too low to make any sense within the context of coupled mode theory. So we've got to keep looking. The answer we eventually came to is to remove the patch from the slot by increasing the patch boundary to infinity. And so in FICA, we model that as 2 infinite ground planes separated by an air dielectric and joined by a probe. and then you've got magnetic unknowns on the U-slot geometry there. So when you run CMA on this, you get kind of what you'd expect. You've got kind of this long slot, you get a half wave current distribution of magnetic current in the slot, and you get constant current on the probe, and you get a resonance right around 912 megahertz, and that fits really nicely within this couple mode theory framework that I'm presenting so far. The other thing you can do is you can use CMA to create actually a real simple circuit model of this resonator that involves the LC resonator of the slot and the LC resonator of the probe. And that goes a long way to explain why this U-slot is much longer than you would expect for 900 megahertz. Another thing you can do is to calculate the normalized coupling coefficient directly from the modal near fields of the patch without the slot and the slot without the patch. And so I've calculated near fields in this volume I've shown here, and I'm going to run that data into this formula, which is an overlap integral of E and H divided by the modal electric energy and the modal magnetic energy. And when you do that, you get kappa equals 0.19. And if we go back to, again, that couple mode theory formula for the coupling coefficient, we get 0.26. And those two numbers are relatively close to each other. And so, again, that's just showing that couple mode theory makes sense for this geometry from more than one angle. Another thing you can do is create some equivalent circuits. And I'm going to use these high pass equivalent circuits from this Jacob Adams paper. And so when you do CMA on the full geometry, you can use the results to calculate R, L, and C value for each mode. Now in the full geometry, the in-phase and anti-phase modes are orthogonal, and so these modes just go in parallel, and there's no coupling between them. If we take that step back and look at the individual resonators, the patch and the slot, we can do CMA on each one and do the same kind of process and get a RLC resonator for each one. But these two circuit models for the individual resonators will need to be coupled by a mutual inductance. And it turns out that the transformer coefficient K in this mutual inductance is equal to kappa. And I'm going to show the results here on this slide. And here's the equations that show you how to get the RL and C values from your CMA data. So here on the Smith chart, it doesn't look like these overlap that great, but if you plot the log magnitude response, it's actually not too far off. There's just a 10% shift. And the reason for that is that in the Huon and Lee design, that patch is the probe is exactly at the center of the patch. And that leads to these very strange values for the patch resonator resonance, 40 mega ohms and a millihenry, and not even a femtofarad of capacitance. And that just makes the circuit model just extremely sensitive. But again, the log magnitude response overlaps well, and you get these W shapes that are real characteristic of these multi-mode patches. Since we did this work on the U-slot patch, we've extended these same ideas to several other multi-mode patch structures, which I'm showing here. And we've got a conference paper on each one of these, so if you email me, I could send those to you. But one of the structures was the E-shaped patch, which is really just a special case of the U-slot patch, where the U has been kind of pushed off the edge of the patch here. But CMA of this structure shows in-phase and anti-phase modes and operates much the same as the U-slot patch. I'm showing stack patches here in the middle, and again, there's an in-phase mode and a anti-phase mode here. And also for coplanar parasitic coupled patches, you've got an in-phase mode where the charge distributions are aligned and an anti-phase mode where they are oppositely aligned. So we're actually giving a talk on coplanar parasitic coupled patches at Asia Pacific Microwave Conference next week. It's a Zoom conference. I don't even think you have to register to listen to the talk, so tune in if you're interested in coplanar parasitic coupled patches. But the overall message of this slide is that couple mode theory is a unifying idea among all these multi-mode patches, and it shows how they're all the same, but also it shows how they're different. And so Again, we'll have to save the details for all these for later. Okay, so to wrap up, I hope I convinced you that couple mode theory accurately describes the U-slot patch, and we actually have a straightforward design methodology that's based off of CMA and CMT, and that's available in the paper here. Also, there's a shortcut link to it right here, and my email's on the slide. Feel free to get in touch if you want to know more. Thanks.
Okay, good morning, good afternoon, and also good evening, my dearest friends. My name is Fenghan from ShanghaiTech University, China, where I am currently a new faculty member. The topic today will be the review of characteristic mode analysis for resonant metasurface antennas. And first of all, I would like to thank for this great opportunities to allow me to present my work here. This is the outline. Starting with a brief overview of the CMA and also Metasurface, then would be the analysis, excitation, manipulation, and also the mode synthesis of the resonant metasurface antennas or resonators. Then would be a short summary of the works presented here and also some future directions, which is of interest in my group. So first is the introduction to Metasurface, because maybe not all of you are very familiar with it. On the right-hand side of the screen, you see a lot of periodic patches. In general, they could be arbitrary unicells of any shapes, but finite dimension. It can be made of dielectric or some metallic patches, crosses, for example. Then the common conditions in the research is including the far field excitation, for example, be the plane wave or cylindric wave incident onto the plane from the left hand side. So then there will be some transmitted wave and also the reflective wave on the right hand side and also the left hand side of the metasurface. The second will be the infinite extension, so that the surface is infinitely extended to infinity, so there won't be any edge diffraction. The third one is that every unicell is electrically small, so the fields vary slowly over one unicell. In that way, the overall metasurface may be the field may be homogenized or averaged, so that the overall metasurface can be presented by a certain boundary condition. The objective to use a metasurface basically it is used as a scatterer in order to manipulate the wave front, either for reflected wave or for incident wave, to change the polarization, the phase, and also probably the magnitude, and also the frequency if some active or nonlinear device is added to this metasurface. But the research gap is like this. In conventional designs, the three conditions are assumed, and the missing part is that the near field interaction between the metasurface and sources. Let's take an example, a very simple example. Let's assume there is a finite metasurface with only a few unicells there. So the behavior may be very interesting, but there is no infinite extension. So in that way, we have the edge truncation effect here. So that means if any wave excited over the metasurface or very close to the metasurface, there will be wave reflected back. So with the, let's say, the left-hand side traveling wave and also the reflected traveling wave, so we may have some standing wave, which is also known as the resonance. The third one is that in addition to the near field excitation here, and also the finite extension or the edge truncation effect here, we may not have a periodic unicells, or we may have some local field difference caused by a via, let's say a feeding via, and maybe some other sources, and we may also have some noise from a chip, from an IC or something else. In this way, we don't have the three conditions, the assumptions. In that way, how we can address the problem that when a metasurface is truncated and close to its excitation source, also with some loading effect or some local field differences. And the proposed method is to apply the characteristic mode theory and do the characteristic mode analysis to the metasurface and see what we can get. So these are some works recently published. So let's see a case study, and we are going to have a truncated metasurface as resonators. Let's assume that we have a 3x3 patches which compose a metasurface very close to the ground plane, and the distance is very short, very small. Let's say smaller than 1/10 of the frequency of interest. And also, let's say just calculate the first 10 modes of the highest mode significance. By the way, the mode significance, when it's equals to 1, means that a mode resonates at a certain frequency. Let's look at this table. So we see a lot of modes. Let's say for J1, J2, the mode 1, mode 2, they resonate around 6 gigahertz, and the rest just a few hundred megahertz, less than 500 megahertz, higher than the first and the second resonance. So it's very different from conventional rectangular patch resonator that for metasurfaces, we have multiple modes. They are very closely spaced to each other, probably due to the capacitive loading of the surface that modifies the surface wave propagation against the frequency. And let's take a look at the electrical currents over all the metallic patches. Actually, they are perfectly electrical conducting. So we have the currents and the very interesting radiation patterns. This is also different from conventional rectangular patch resonators because we see the modes, let's say the electrical monopole, the fourth mode, and we may also have an electrical loop, which forms a magnetic monopole, which is here, the fifth mode, the loop mode, and so on. Is it a TM10 mode or 01 mode? In order to figure it out, we can plot the fields between the metasurface and the ground plane, and we see that it's different because for the third order mode, for rectangular patch, we have the currents over the patches. We have the left, right, left. We have an antiphase current. We have a main lobe on the broadside at the broadside direction, and we also have the side lobes. But for this metasurface, we can find actually one resonance under each unicell. So overall, we have 3 variations in terms of the normal E field along the resonant direction. And all at the same time, the conventional, the TM03 modes still exist there. This is also different from conventional rectangular patch resonator. If we take a closer look at this distribution in terms of the charge and also the currents, in fact, we have an array of resonators. So I believe that this somehow explains why the first order mode is the TM03 mode instead of the TM01 mode for the overall metasurface. The second is we're going to consider the coupling when it couples to a near field source, not only to the source but also the supporting structure. Let's say a slot. These are not the 4 dipoles, but 4 slots cut over an infinite ground plane, like just look like this. And we analyze using the CMA as well. We find we have 4 modes here at the lower frequency, and they have a different symmetry, very closely spaced. So when the slots close very close to the metasurface, what we have is here. Pay attention to this frequencies. The resonance is about 4.5, between 4.5 and 5 gigahertz. But here we see that the modes of the slot, they shift to lower frequency. And for the metasurface, they shift to the higher frequencies. So we have the important conclusion that when they put together, they have very strong effect to each other. And in this case, CMA provided a very, I would say, insightful analysis tool to reveal all the insights, or say the model behavior, what happens there is just like a microscope that allow us to take a very closer look into the resonator itself when the two resonators they are coupled to each other. So the next is that we are going to consider how to excite them, because we have so many modes, but we may not want all of them to be excited. Let's say we want to excite the first modes of broadside radiation for dual polarized application, and we can also excite the slot mode so that we can combine them for broadband applications. The question is that why we add the slot here. The basic idea is that the field produced by the excitation source, for example, the slot here, this is the E field in the near field region. The field should be matched to the field of the mode of interest in terms of frequency, polarization, and phase and magnitude. If we put this slot somewhere which is similar to the field radiated by this mode, we should have this mode being excited. So the optimum position should be where the normal E field changes direction. So we have 1, 2, 3, 4, 5. So in order to have a symmetric field distribution, we could put this slot at the very just underneath the center patch. And once we do that, we could see that if we calculate the far field radiated power and decompose them to each mode, we have a slot mode at a lower frequency. Also, the metasurface mode, the fundamental mode at higher frequency. The conclusion is that the antenna works with the slot mode and also the extraordinary TM03 mode of the metasurface for bandwidth enhancement. Let's say the impedance bandwidth and also the gain bandwidth. To summarize a few excitation methods, first we have the slot coupling. We can make an antenna array, just put the slot in the right position. Then we also have the probe excitation, and we also could have the electrical currents just very close to the metasurface. Then in this way we use the electrical currents coupling. And there are also works where the slot array made by the substrate integrated waveguide, the SIW technology, to excite this metasurface at high frequency, and also a low frequency slot, just use the rest of the aperture to excite integrated low frequency resonance to make it for a shared aperture antenna, and also surface wave coupling. So we could excite them as good antenna for radiation. But there are still some modes. There's modes when this antenna, when they are put close to each other for MIMO applications, then we may have some problems. The wave radiated by the primary antenna, let's say the antenna 1 or port 1, will generate induced currents over antenna 2. And also there's antenna 2 where the induced currents will radiate and reflected back by the ports. And also the reflected wave will re-radiate and also generate secondary induced currents on the original antenna. And all the fields they sum up will result in very poor isolation, not only the port isolation, but also the polarization isolation, and will also cause a pattern distortion for decrease the signal noise ratio. And we did a simulation to see this. When we only have one antenna, which is the electrical dipole excited metasurface for wideband application, we have the red curve, dashed curve here. This is the isolated one antenna. But when we put them all together with a center to center distance about half wavelength, in this way, I think it should be slightly more than half wavelength, but less than 0.8. In this way, we see that impedance matching is hardly changed if we only excite port 1, but with the port 2, 3, 4 connected to the match load. But if we look at the directivity, they are quite different. For the MIMO application, we have a fluctuation of gain due to the pattern distortion, which is shown here in a 3D plot. But if we look at the electrical current distribution over the common ground, we see that the ground under the antenna 2, antenna 3, antenna 4, they are also excited. And this current should also be a summation of all the CMs which belong to the antenna 2, 3, 4. So in that way, we know some higher order modes have been excited because the currents they are of in antiphase. In order to restore or recover the distorted patterns, we are thinking about to suppress them. And what we did is that first of all is to suppress the x-directed currents. In this way, we cut the slots onto the unicell. So the resonant length in the y direction is almost unchanged, but in the x direction, the electrical length of each unicell is much shorter. So we believe that these modes are shifted to much higher frequency outside of the screen. So in this way, we call the first method is called the mode shift. And the second is that if that's not enough, for the rest of the mode, we would like to change the polarization. If you remember, the mode excitation coefficient is defined by the inner product of the impressed field and also the mode currents. So if we put them to be orthogonal in terms of polarization to each other, we should have a very small excitation coefficient, even though the mode is still there. So if we put the selectively shorting some of the unicell to the ground, the current will be mostly concentrated over on the surface of the vias. In that way, we will have a quite small mode excitation coefficient for the unwanted modes. For more detail, you can check these papers, which will be listed in the last a few slides. So after that, we see that if we compare the original pattern and the decoupled pattern, or say the improved patterns, we have quite a significant improvement. And for the current over the ground plane, we also have the rest of the antenna 2, 3, 4 being quite neat in terms of the current distribution, or say we could say antennas 2, 3, 4 they are almost invisible. We just put the polarization in turn. In this way, we could also, without losing the ability to form durable applications. If we compare to the dipole, just a quarter wavelength over a ground plane, the proposed antenna also has a better gain. And compared to the original antenna, we don't have the fluctuation. Then the next is usually the questions asked by our reviewers is how to design a mode at a desired frequency. You basically did some parameter guess and some optimization to find the mode resonant frequency, basically to put the mode at the frequency that we want. And since the metasurface is usually very large and the unicell is very small, the characteristic dimension is very small, usually defined by the minimum length of the unicell or width of the unicell or the slot width between the unicells. So the characteristic length is very small. So usually we have a very large number of meshes, but how to reduce the time for CMA, because it takes quite a long time. And then also, how do you know which unicell is the best unicell? Why you always use patches instead of some cross? And these questions are very inspiring. For that, I really would like to thank our anonymous reviewers to pose this inspiring questions, which actually becomes the motivation of this work. For mode synthesize to answer these questions. Previously, we have a full structure, then we guess, we optimize until we get the modes at the specific frequencies. And we are thinking about how to get the optimum. But the first question is there really an optimum structure for a certain design? So to answer that question, we make use of one of the most powerful aspect of metasurfaces, that we can do the average of the fields over one unicell, so that the overall metasurface can be presented by homogeneous impedance, maybe a boundary condition. And here we use the impedance boundary condition. What we did is that we assume there is a homogeneous, very thin, of infinitely thin sheet, and this sheet has a sheet impedance. So in this way, since it's homogeneous, so we don't have to calculate, we don't have to care about the characteristic, the dimension of each unit cell, but we can use very sparse unit cells to reduce the time used for characteristic model analysis. So we have an ideal homogeneous sheet here, and then we can only optimize the sheet impedance to place a mode at a certain frequency. Only after that, with this impedance, it's only one number. With this number, we can just optimize one unit cell to achieve that sheet impedance. Then in this way, we think that the modes should be able to recover. That means the modes of the realistic structures should be similar to the modes of the originally ideal impedance sheet. And in this way, we look at the ideal sheet first. If we tune the sheet impedance to capacitive, or inductive compared to a perfect conducting sheet, which is actually has a sheet impedance of 0, we can tune the resonant frequency. So we can only just optimize the sheet impedance, and we calculate the modes, and the standard is that we put the first broadside radiating mode of in-phase currents at 6 gigahertz. The next is that we want to link the homogeneous model to a realistic model. Let's say we still use patches, and we have ZS, because we can tune the ZS here to tune the resonant frequency. We have one number, which is the sheet impedance here, and we use the patch unit cell to find the dimension of the unit cell until the gradient impedance of the unit cell approaches this ideal sheet impedance. So we have the real structure, and we do the CMA of the real structure again, and we compare the ideal case and the realistic case. We find them, they are very, very similar to each other, excluding the bandwidths, because in a realistic model we have the frequency dispersion, but in the ideal model we don't have that. And if we compare the currents, they are also very similar to each other. So we think we are successful. And then the contribution is that later on, we don't have to have this realistic model when we try out different excitation schemes. We can just do the excitation based on ideal sheet in order to reduce the calculation time, the design difficulties. Only when we success on the homogeneous model, then we apply the same excitation method to a realistic model to improve the design efficiency and also the success rate. In this way, we put the dipole here. So we can excite 3 modes if we look at the decomposed radiated power. These are the antenna that we made. And the dipoles, the wires, they are connected by balloons to the feeding source. And in this way, we achieved the 45% of impedance bandwidth and also the radiation pattern bandwidths. To note that there is the side lobe for the high frequency, which is actually a TM21 mode, and there are more E field and H field plotted for this current and for all of these modes, so that we know that the first mode is the dipole mode, the second mode is the TM10 mode, and the third one is the TM21 mode. This is different from the previous metasurface resonators where a TM10 mode is formed for each unit cell, but since here the unit cell is very, very, very small, so we have the overall effect, so that the first fundamental mode of the metasurface is the TM10 mode, and the second here we cited is the TM20 mode. I'd like to give a short summary due to the time limit. So if we look at the development of metasurface technology, starting from the far field region, then gradually goes to the near field region, but it's a radiative near field region to form different near-field patterns or field patterns, field distributions. And if when the metasurface is very close, very further goes closer to the source or another structure, we may have to use the characteristic mode to analyze, to involve this coupling in between, and in order to find the more detailed mode results for excitation for antenna purpose. And the summary also goes for the challenges and opportunities. So far, we only look at some of the fundamental or lower order modes. There are also many higher order modes there. So how to selectively and effectively excite some of the higher order modes is still of interest. The second is the application of CMA and also the combination with Metasurface to apply them in a more complex and or more realistic systems. For example, when the slots and dipoles are not applicable, and also when the metasurface is the electric size is larger. The third one is that like for simulation purpose, we would like to have waveguide ports, especially for the higher order modes. In that way, we still need the development of theory and also the CM formulation and the modeling. To my best knowledge, that for at least for commercial softwares, the modeling of waveguide ports for CM theory is still not available. And also to take into consideration of finite loss, for example, the effect of human heads for the TWS, the true wireless earbuds, and also for hearing aids compatibility, and also for the design of hearing aids antennas, and also smart watches and more wearable devices. The last one, but not least, is how to do the model analysis for periodic structure. In this topic, Dr. Wang Chaofu from National University of Singapore has done some job. So these are some of the references and also related works in this presentation. And lastly is our very beautiful campus in Shanghai. So you are very welcome to visit us. So thank you. If there are any questions that I would be very happy to answer. Thank you very much.